coming for our this spring meeting for the seminar, Carolina Math Seminar. Today we have totally 6 speakers. The first one is a student from our school, sophomore, Josh Smokes, and his talk is about an identity for X-ray eye.
I'm Josh Moe. I'm from USC Salkehatchie, and this is my presentation, An Identity for X-Ray Eye. Every so often in Dr. Lott's independent study class, we'll solve a problem from the American Mathematical Monthly. You can't see it here, but this one is from the October 2011 issue, volume 118, number 8, problem 11596. And the problem is, let A, B, and C be the side lengths of the triangle. Let RA, RB, and RC be the corresponding X-ray eye. We want to prove that the left side, the sum of these 3 fractions, equals 8 times this fraction squared minus 2. Before we can solve it, let me tell you a little bit about what X-ray eye are. For any triangle, you have a triangle here, ABC, it's in black. You can always find an inscribed circle in blue. And if you extend all the sides of the triangle, like here, you can find a inscribed circle tangent to 2 of the extended sides and 1 side of the triangle. You can find the center of the described circles by using the internal and external angle bisectors, here in green and red. After you find the center of your described circle, your X-ray eye is going to be from the center to the tangent line. That's what X-ray eye are, and that's what we're trying to find an identity for today. To solve the problem, to prove it's true, we needed a couple formulas. First is Heron's formula. K represents the area of the triangle, and S represents the semi-parameter. And we also needed a formula for X-ray eye, which we got from Johnson's Advanced Euclidean Geometry, which is RA, RB, and RC equal K over S minus the corresponding side. Now, we needed this formula, but we also needed it in a little bit different form, so we had to change it a little bit, and that's what we did here. We derived these 3 formulas. First, we just multiplied 2 into the top and bottom, and we used the sum of A, B, and C to represent S. We simplified it, we did this for all 3, and it got us these 3 formulas. We also needed to use it in a different way, so we took K and replaced it with Heron's formula here on the board, and we put our denominator into our square root and simplified it, which gives us this. We did it for all 3. We're going to use these later on to solve the problem. First, starting with the left side, we substitute RA, RB, and RC with the second formulas we derived here. As you can see, the squares and square roots automatically cancel each other out, so we have these 3 complex fractions. After that, we simplify the complex fractions by getting rid of the denominators. That gives you these 3 fractions here. Then we found a common denominator for all 3, added them together, simplified, which gives us this stuff. We denoted that that's equal to L, because we're going to use that later on, a little easier to do simple. So this side is equal to L, we get this big fraction, and then we're going to move on to the right side. From the right side, we take RA, RB, and RC and substitute it with the first formula that we derived here, which gives you this big fraction. And we got rid of the complex fraction, which gives you this step here, and we divided the whole parentheses by 2, which got rid of your 2 up top. And substitute A plus B plus C with S after you divide by 2 is equal to the semi-parameter formula. And that gives you this. We then substituted K with Heron's formula again, which gives you this step. In the next slide, you'll see we moved our denominators up into our square roots and simplified, which gives us this. The next thing we did was squared it, which doubled our terms and gave you these 6 terms here. Everything inside of your square roots over here is squared, so they automatically cancel out your square root. And we multiplied 8 in, which gives you this step. We then wanted to find a common denominator for all 6 so that we could add them together eventually. We found a common denominator which was equal to k squared. Aaron's formula squared, so pretty much without the square root. We factored out our denominator, and so we have 1 over k squared times what was left of our numerator, which is all of this. And the next step, we broke up our 4's into 2's, and we grouped all of our squares. And it got too big to write to put in the PowerPoint. So we have this. Like I said, we grouped all of our squares into a single parentheses, and we broke up our 4's into 2's, which gave us 6 2's. 1, 2, 3, and the last 3 here. As you can see here, you have these 3 terms, which is pretty much a squared plus 2 times something plus b squared, which can easily be factored. For all 3 of these terms, we factored them, and we got these 3 terms here. First red line is equal to the first red line, second, third. Factor it, gets you up this step here. The next thing we wanted to do is factor out all of our common terms. Factor out s minus c from here, s minus a from here, and s minus b from here, which gives you this step. And you still have those three groups of 2's trailing. And to get rid of that, we brought our denominator back in, k squared, and we multiplied k squared into our 2. After subtracting it and simplifying, you can see that all 3 of these 2's cancel out with the minus 2 here, which gives us this, and we denoted that as equal to r. And back to the problem. Which gives you this line, and that is equal to r. When you put this line next to our L, you will see that L is equal to r. Those 2 fractions were the same, and therefore we have the left and right sides equal. The sum of these 3 fractions was equal to 8 times that fraction squared minus 2. So the original equation is true, proving that it is an identity that can be used for x-ray dot. That's my presentation. Thank you. Any questions?
So, you said that you sent down to the American Mathematical Journal, right?
Yes, sir.
You have heard something about the decision or not yet?
The what?
The decision. They are going to prove this or
Oh,
is it?
we proved it and we sent it in.
Oh, you don't know
We have
yet.
not gotten the response yet.
Okay.
Never heard it.
Can you go back to the picture first?
The picture? That one? Or-
Oh, yes, that one.
Right here?
Okay. It looks to me like Apollonian circles. Have you tried to extend that result to Apollonian circles? It looks very familiar,
Right.
right?
Very similar to that, but we didn't extend that. Actually, this problem, we got this problem from this book, so I directly tried to let them try to survey all these kind of property only for the X-ray dot. So
Okay.
they only focus on the X-ray dot.
You should search on the Apollonian because you can extend that problem to a more interesting problem.